Hey guys, it's Justice again, and welcome to another video. In today's discussion, we're going to talk about the quantum Fourier transform and the quantum phase estimation algorithm. Now, this particular video is going to be part one of a two-part series in which we go through a derivation of the quantum Fourier transform operations itself. In particular, we're going to describe the mathematical derivation that walks through why the circuit construction is the way that it is and why it works. And then in the second video, we'll talk about applying the quantum Fourier transform in the quantum phase estimation algorithm. Now, in particular, the quantum Fourier transform, or QFT for short, is of large interest to a lot of people doing algorithm development because it was one of the early signs of a theoretical superpolynomial speedup in quantum algorithms to outbeat classical algorithms for certain tasks. During this discussion, it'll basically, I'll go through the mathematics and talk step by step exactly how the mathematics plays out to give a little bit more intuition to why the quantum Fourier transform works the way that it does. I know that this was really helpful for me as I was learning quantum algorithms and quantum computing, and so I hope that it's helpful to all of you. So first, I'll go through some of the resources that I used. I used the Mike and Ike book, An Introduction to Quantum Computing by K. Laflamme and Mosca, Problems and Solutions in Quantum Computing and Quantum Information, and Mathematics of Quantum Computing, an Introduction. This last book is actually really helpful. It kind of walks through a more rigorous description of the mathematical derivations, and it gives a lot more context in exactly what laws are applying, what rules are applying. So diving into things, the quantum Fourier transform, as I've written it here, is very similar to what's known as the discrete Fourier transform or even the classical Fourier transform. Now, what is the Fourier transform supposed to do? Or especially the quantum Fourier transform? Well, it's no different than the classical version in which you're basically taking a particular state space and wanting to represent it as a superposition of its conjugate state space terms or components in a weighted average. So, for example, if you have a time-varying periodic function, you can represent it in terms of its conjugate variable in frequency space. So any time-varying sinusoidal curve can be represented by a single term in frequency space. And so the operation in order to get us to the quantum Fourier transform or to map this state x into a superposition of states k will be this expression here, in which basically the way that we can change the basis is that we'll have an outer product of the ket k with the bra x, and that'll essentially serve as a projection operator. And then just as a word to notation, walking through the rest of the derivation, x and k in general are an n-wise bit string where each bit contains either a 0 or a 1. So that's just kind of something to note. And then another thing is binary representation, which I have written out here for both states k and x. And the way that binary representation works is that you can think about it analogously to the decimal system, in which you have the ones place equal to 1 times 10 to the 0, and then you have the tens place as 10 to the 1, etc. In binary representation, it's a base 2. So that's just kind of a simple way to explain it, but this is how it works in computer science, and we'll just kind of keep that convention. So now kind of walking through the mathematical, the derivation of the quantum Fourier transform, we're just going to act the quantum Fourier transform on state k, or state x, I'm sorry. And so it's written out in the following way, where we have the operator just stealing from the expression that I have above here, and then multiplying it by a state x. Now, because we're assuming a complete orthonormal basis set, we're going to have x times 1, or x, the bra x times the ket x equal to 1. So it's normalized. And so then what this reduces to is this expression in the purple. And so just going through step by step, I'm going to walk through what each line of math says. So going from line 1 to line 2, all we're doing is writing out the state k in terms of its bit string representation. And what that bit string representation is just stating the bit 0 all the way through the n-1th bit. And then I'm expanding the summation in terms of each bit. So when you're looking at the entire bit string representing 0 versus 2n minus 1, where n is the number of bits, really all that is kind of going through each change of each bit. So basically you have all zeros, and you have all zeros and then a 1, and then you have all all zeros except for the second to the last bit, and so on and so on and so on. And so moving from the second line to the third line, I just write out the k in terms of its expansion. So we have k sub l times 2 to the l. And then going from the third line to the fourth line, we're recognizing the fact that, or I'm simply just kind of compacting notation here. So all I'm really doing is taking the multiple summation terms and putting it into one, but still representing the exact same thing. And now moving to the between the fourth and the fifth line, just using the law of exponents, since there is a sum in the exponent, we can represent that as a product series of exponential terms. So this product symbol is denoted here, and we'll multiply all these exponential terms, and it will be equivalent to the summation in the exponent. And then lastly here, assuming that, in general, you might have some familiarity with tensor notation and direct notation, moving down to the sixth line, we have this tensor product series, which is equivalent to this bit string representation. So it's just the way that in quantum computing, we're able to represent multi-qubit states. And so each qubit having a state KL and doing that product throughout. And then in the last line here, you might be wondering, well, in general, you can't just take the tensor product out because the order of the multiplication matters. So addressing that, I'm going to take just a moment here to go through exactly how this would work. So based off of our previous note, we have a summation, we'll say, of x equaling 0 to 2n minus 1 x. And then if we want to rewrite that, we can write x0 xl equaling 0 all the way up to 1. Then we have cx, and then we have a tensor product from l equaling 0 to n minus 1 x sub l. So really what this is doing is taking the state x, saying that we'll write it out in the following way, and then rewriting it similar to how we wrote it before. And so what this is saying is that if we were to kind of expand this, we'll say we have x0 equaling 0 to 1, and we'll take the cx out. So we have the summation, and then we have x0, and then we have tensored with another summation, x1 equaling 0 to 1, x1, ... 0 to 1, xl. Now, if we look closely at what this is, it's, if we look at one term in particular, this one term is just the 0 state plus the 1 state. And if you notice, because this is all that the states xl can take, these are the only possible states that can come about. So if we look at this entire series, we just know that this is this expression. So because the order doesn't really matter, because we're just doing a tensor product series of the same terms, that's the only way that this can actually work out. So going back to the derivation notes, so this is kind of where we stand, right? So now that we've written that out, we're going to take another step to expand the x-bit string. So all we're really going to do is just take the binary expansion and plug it in. And so we see that in the exponent, we now have the summation term. And then we're going to leave it there, and then we're going to add the 2 to the j and multiply that times the 2 to the l minus n. And so what we end up with is kind of expanding this out, and then we get down to the bottom where I'm just purely expanding out the summation for the KL state in terms of the 0 state and the 1 state. And the only reason that the coefficient for the zero state is 1 is because KL in that case is 0, and therefore the exponent is 0, and so the coefficient will be 1. So now the next step, we're gonna pay a little bit close attention to this term and do something a little clever. So what we're gonna do is we're gonna split up the sum in the exponent into halves. So we're basically gonna have the first half going from j equals 0 to minus L plus n minus 1, and then we're gonna have the second half going from minus L plus n to n minus 1. And so if we look at this red term here, we can find something interesting. Based on the range of the index j, this coefficient 2 to the L minus n plus j will strictly only belong to the set of integers. And since that's the case, the form of that exponential term will then take the form of a constant multiple of I to the 2 pi. And so all you're really going to see is just constant coefficients of 1, because e to the I 2 pi is 1. So then the only term remaining is the term that I have in blue here, and I've rewritten here. So we have j equaling 0 to minus L plus n minus 1. And so plugging that back into the full expression, we have this. And so now if you go through the counting and start to think about, okay, well, what does this look like for each qubit, right? Because we want to start to understand exactly what are we doing to each qubit? What is the state that we're looking to get out for each qubit? If we look at the last qubit, or the L equals n minus 1th qubit, then we'll notice that we only have one term. And that one term is going to be the 0th bit, the 0th x bit, so x sub 0, divided by 2. And so that's all that's going to be represented there. But now if we go to the 0th qubit, and the difference between the n minus 1th qubit and the 0th qubit is primarily a convention in terms of how you're organizing your particular algorithm to account for the qubits on your QPU. But if we look at the 0th qubit, then we'll notice that it has all n terms in the expression. And so here we're going to take advantage of something called the binary fraction representation, where instead of weighing a sum of binary components from 2 to the 0 or 1 to the nth power of 2, we're going to focus on negative powers of 2 and sort of just kind of modulate the binary fraction, the binary representation. And so once we've done that and we plug in and we notice the fact that the superscript, or the exponent of 2 is purely going to be negative, then we can leverage this expression of binary fractions and write out our terms in the following way. So you notice here that the n minus 1th qubit only has one term, x sub 0, whereas as you count down to the 0th qubit, you'll start to have all the terms in the binary expansion. And so then now I want to kind of draw our attention to the circuit construction, which you can find in any quantum computing textbook. What you'll see is that you have a Hadamard gate multiplied by a controlled rotation in the following series. And you also see these terms on the right, which looks similar to what we're doing up here. But let's get some intuition behind why exactly that's working. So in particular, if we take the Hadamard gate and multiply it and act it on some random state x, we know that we can write out that state in the following way. But another way to write this is this. And so lastly, we can kind of wrap that up by saying EI 2 pi 0.x1. So another way to say this is that, applying the Hadamard gate for this 1 qubit state is the Fourier transform of that 1 qubit state. But now let's go a little bit further to a 2 qubit state and actually look at what this controlled rotation does. So if I were to write out 2-qubit circuit, do the first component here. And let's say that I denote the input state this way. And then we'll look at the state after the Hadamard and the state of this circuit after the controlled rotation gate. And we're going to define the rotation gate to be equal to this. The reason why I've written the exponential term in the lower diagonal is for a reason that you'll see a little bit later on. But right now, let's just actually kind of step through this. So at state 1, at point 1, this is what we've done. We'll add the Hadamard gate in this first space and then the identity on the second. So we have x0, x1, I, and this will give us 1 over square root 2, state 0 plus e to the I 2 pi 0.x0. Then tensor that with x1. And so all we're doing is just simply taking the definition that we had up here and applying it down here. And then at point 2, once we've applied the controlled rotation, we can write out a controlled rotation in the following way. So we have the identity applied if the 0th qubit is 0, and the rotation if the, sorry, I think I said the 0th qubit, I mean the x sub 1 qubit, if that qubit is 1. And then we're acting that on x0, x1 after state 1. And then we'll go ahead and write this out. And so what we end up getting is 2 terms. So we have the identity applied here. And the reason I've written it the way that I have is because the projection of the x sub 1 qubit on the 0 state is what's going to contribute to this term in particular. And then we'll add one more term. So here we have the R gate applied to 0, and then we have I 2 pi 0.x0, 1, tensored with projection of the x sub 1 qubit with the 1 state. All right. And so when we think about how this R gate acts on the superposition of these 2 states, we can say that it works in the following way. We have a summation of states going from 0 to 1, and then we have some coefficient CZ. What ends up happening is that we'll get a summation of e to the I 2 pi, and then we'll have z over 2 squared times CZ z. So now if we work this out for the 0th term, so let's say if z is equal to 0, then the z in this exponent here turns to 0, and then this whole exponent is 1, and then you're left with the coefficient of CZ, which in this case is also 1. So then we get 0. But then if CZ, or if state z is equal to 1, then what we get is e to the I 2 pi 1 over 2 squared. And then we can also write out the other exponential term, 2 pi, and we have x 0 over 2, 1. And so then if we were to put the term together put these expressions together for the second term, but then if we use our binary fraction expansion, then we know that this term in the exponent can be rewritten as and so if we were to look at the first term, you know, we get a similar output, but in that case, the second term in the sum here would be 0. So we're able to write in general this 0.x sub 0, 1. In general, we can write it in this way. Because the controlled rotation will actually carry this term, whether or depending on whether the control qubit is 1 or 0. So it will effectively do the same thing. And so that kind of wraps up the derivation mostly. And so what we can now see is that we understand exactly why these expressions look the way that they do, and we've essentially verified that this circuit construction will indeed implement the quantum Fourier transform the way that we want it to. So I hope that was helpful, and I look forward to seeing you guys in the next video on the quantum phase estimation algorithm.